If we look at the standard just prior to this one, 6EEB7, it deals with equations in the form x plus p equals q and p times x equals q. So they're very simplistic equations that just involve one operation. Looking ahead to grade 7, students will have to deal with inequalities in the form px plus q is greater than r or px plus q is less than r. So notice that the complexity level goes up a notch because these inequalities have more than one operation involved. So we have to address this. We have to get students ready for that complexity in grade 7 by doing some things here in grade 6. So according to this standard, 6EEB7, we have equations that are strictly one operation involved. For example, just adding or multiplying. But here's something that's very important. Non-negative rational numbers. It's not that big of a factor with equations, but it is critical with inequalities, in particular when you're dealing with multiplication or division. As you know, when you have an inequality, if you multiply or divide by a negative, that involves switching the inequality sign around, and that's a lot more complexity. But that is not an expectation here at this grade level in grade 6. So again, p, q, and x are non-negative. They're positive numbers, which makes a huge difference when dealing with inequalities. Let's say we have d plus 5 is less than 12. Now the process here is very similar to what you would do for an equation. We want to isolate the variable, so we need to subtract 5 from both sides. So we would have d plus 0 is less than 7, or just d is less than 7. And then the number line diagram would look like this. We know that it does not include the 7, and it's all the numbers to the left of 7 because it's all the ones that are less than that number, 7. Let's try this example. 3d is greater than 12. We have to isolate the d and get that by itself. Some might look at this as having to multiply each side by 1/3. Others might see it as dividing both sides by 3. But either way, we're going to arrive at the same place. So we would have d is greater than 4. We've isolated our variable. And the number diagram would look like this, where it doesn't include the 4, and it's everything larger than 4. Now let's address this critical idea of representing a constraint or condition in a real world or mathematical problem. And this is something relatively new. Let's look at this example. Manny has a sales job and gets paid on commission. This week he wants to earn more than $700. So we know that the number line diagram would look like this. It's more than $700, so it doesn't include the 700, and it's everything to the right because that's everything that's larger than 700. We have to pay attention to the exact wording on these statements. What if it said that he wants to earn at least $700? Students might look at this and focus on this idea of least and might think that, well, is it everything to the left of 700? Or is it everything to the right of 700? Well, simple test. Try numbers on each side and see what works. Let's see, 600. No, that's not at least 700. So no, that doesn't work. How about 800? Yes, that's at least 700. That works. So we know that it's everything to the right of the 700. But now we have a question of, okay, wait a minute, does it include the 700? Well, at least means that much or more. So it does include the 700. So we need to have a darkened end endpoint to indicate that 700 is part of the solution. Let's look at another example. Safety rules limit the average work week for truck drivers to 70 hours. So the interpretation here would be that a truck driver can drive no more than 70 hours per week. Or maybe a slightly different interpretation would be that a truck driver can drive 70 hours or less per week. So the number line diagram should look like this, 70 hours or less. And since it's 70 hours or less, it does include the 70. That's another big decision, so we have to have a filled-in endpoint. Let's go back and look at that first example about Manny and the sales job. Here's our number line diagram, and mathematically that would be x is greater than or equal to 700. Although mathematically correct, is that really realistic? For example, could he really make like $20 million in that week on commission? So it seems a little bit unrealistic for him to be able to make $20 million. Let's look at the second example with the truck drivers. Here's our solution, our number line. And numerically, mathematically, that would be x is less than or equal to 70. Now, based on our solution, negative 23 hours could be part of that. But you can't drive negative 23 hours. Realistically, 0 is as small as we can get here. A truck driver might take the whole week off, so he drove 0 hours. But that's it. We can't have any negative numbers. So really, for this situation, there's two conditions that have to be met. The number of hours that a truck driver can go has to be 70 or less. So that's the first condition. But since we can't drive negative hours, the number of hours has to be 0 or more. So if we look at satisfying both conditions, here's where we are. It has to be everything from 0 to 70. And so that's the realistic solution here. Okay, now these two conditions, the number of hours has to be greater than or equal to 0, but they also have to be less than or equal to 70. So we know that the number of hours is going to fall somewhere in this interval. And in plain English, we know how to state it, that the number of hours, the h, is a number from 0 to 70. But we have a problem. How do we represent this mathematically? In the standard, they only talk about x is greater than c or x is less than c. There's nothing to handle something like this that actually has two different conditions that have to be met. The standards don't address this. How do you express this? Well, let's see. The first condition is the number of hours has to be 70 or less. The second condition is that the number of hours has to be 0 or more. In order to express this mathematically, here's a problem. The inequality signs are opposites. On the first one, it's greater than or equal to, but on the second condition, it's less than or equal to, and we can't have that. We've got to have them both going the same direction. Typically, we like to use less than, so let's figure out how can we make both of these into less than statements. Well, no problem on the right-hand side. We already have h is less than or equal to 70. It's the left hand where we have to do something. Well, let's look at this numerically. We can say 15 is greater than 0, but another way to say that same exact thing is that 0 is less than 15. So we can take that statement, h is greater than or equal to 0, and state it differently. We can say 0 is less than or equal to h. And now by doing this, we have both our inequalities going the same way. They're both less than or equal to. So now, we know where the number of hours has to fall. How do we express this? Well, here's what we do. We can actually do this visually, where what we have to do is combine these two into one statement. Well, let's do that. We'll just move this over. And there it is. This is how you express this type of situation. 0 is less than or equal to h is less than or equal to 70. Now that doesn't sound too good mathematically. It kind of gets jumbled up. In plain English, the way to interpret this symbolism is that h is a number from 0 to 70. Now what if it didn't include the 0 in the 70? Well, all you have to do is get rid of the equal part of it. So you'd have 0 is less than h is less than 70, but that gets a little bit lost in the translation. It's better to look at this and read that as h being a number between 0 and 70. And the word between indicates that it doesn't include either of the endpoints. It doesn't include the 0 or the 70. Since this is not addressed anywhere in the standards, it's going to be a school or a district decision as to when this representation should be taught. Again, it's not in the standards, but this needs to be taught at some point. But again, it's going to be up to the district or the school to make that decision as to when it's most appropriate. In looking at the standards for mathematical practice, doing the activities that we did in this standard, the first 4, we would be doing all of that. Students would have to make sense of problems and persevere in solving them. They have to reason abstractly and quantitatively. They have to construct viable arguments and critique the reasoning of others. And we did model the mathematics. Looking at the other 4 standards, students would be attending to precision, and they would look for and express regularity in repeated reasoning.